Basic elements such as zinc, magnesium, iron, calcium cannot be manufactured. They can be combined to form compounds, but they cannot be manufactured from something else. So where did they come from? To answer this question, we have to go back in time a little bit. The Big Bang occurred 13.7 billion years ago and created the known universe. Also basically creates hydrogen with a little bit of helium, the two lightest elements. While the universe was expanding, gravity was acting on the hydrogen, causing the particles to move closer together to form clouds. The clouds densified and heated up in the process. So once the fusion started by the heat that was created, the fusion started to join the hydrogen elements together to form a more compound element called helium. And a little bit of energy was there as well. Our sun produces every second, burns every second, 6 million tons of hydrogen, transforming it into 596 million tons of helium. Where did the 4 million tons go, you might ask? They were transformed into energy, just like heat and light, based on Einstein's famous equation, E equals mc squared. The 4 tons equal the weight equivalent of 10 supertankers filled with oil, or 13 times the New York population in weight. This is a lot of stuff to burn, even for a star that is our sun 100 times Earth diameters across. This weight loss creates a huge amount of energy, equal to 4,000 light bulbs on every square inch of the sun's surface, or 1 million times the total amount of energy used on the world per year. Now that's a lot of stuff to burn. This energy creates a pressure that is sufficient to hold gravity back, trying to collapse the star any further. So while the fusion process is working, gravity is held at bay, and the star maintains its shape. At one point, all the hydrogen in the core is burned into helium. At this point, the fusion process stops, gravity takes over again, and the star starts to contract. The increased temperature allows to manufacture higher elements in a periodic table. The periodic table lists all the elements in order of its mass. This relates to the numbers of protons in the nucleus. This process is able to manufacture elements all the way up to iron, which has 26 protons in its nucleus. Until you reach iron, you basically create energy out of nothing. Elements higher than iron require more energy to be put in order to get the fusion process started. And there's just not enough energy around. So once a star has gotten to the point where its core is made out of iron, the fusion process will stop. Gravity will take over again, and the star will quickly collapse. For smaller stars, this can be stopped by what is known as the Pauli exclusion principle. Wolfgang Pauli was a physicist who discovered that electrons could stop gravity from causing any further collapse of the star. So the star stops making fusion, it cools down, and continues to glow as a white dwarf for a long, long time. But for bigger stars, gravity is sufficient enough to overcome this challenge. The outer layers of the star will collapse on a hugely energetic core and result in a cataclysmic explosion of astronomically proportion, named supernova. The energy of a supernova is colossal and all spread out in a matter of days. It is during this time that higher elements than iron can be manufactured, like the gold in my wedding ring. Meanwhile, the remaining core from the supernova explosion is continue being crushed. There are no atoms. There are no spaces between atoms. The core turns into a quickly rotating neutron star. 1 tablespoon of the star material weighs as much as 900 pyramids of Giza. The reason it rotates so quickly is the same principle that ice skaters use to do their rotation. They may start with their hands, arms wide spread out, and once they draw it in, the spin increases due to conservation of angular momentum. So if the radius becomes smaller, the velocity increases to compensate. This is what happens in a neutron star. At this point, a different version of the Pauli's exclusion principle comes into play, where 2 neutrons cannot have the same state of matter and will stop gravity from collapsing the star any further, unless the star is so massive that it can overcome this last barrier. If it does so, there's no known physics that will prohibit the star from getting ever denser until it forms a black hole. A black hole is a singularity because it has no dimension. But what about the remnants of the supernova explosion that were posited out in space? Gravity will act among them, pull them closer together to form the basis of a new star, and the whole process will start all over again. Thank you.